The ideal gas law is represented by the equation PV equals nRT. We're going to look at each of these variables because right now this just looks like a confusing mess of 5 different things, but it's actually very comprehensive and incredibly useful. P stands for pressure. V, volume. N is number of moles. And T is temperature. Each of these variables has a specific measurement. Pressure will be measured in 2 different variables. One is atmospheres, abbreviated ATM. Atmospheres are incredibly useful just by virtue of being really comprehensive. How much is 1 atmosphere? Well, it's about the pressure I'm experiencing right now. How much is 2 atmospheres? Well, it's about double this pressure. Nice and comprehensive. But the other unit of measure is a lot more clean when we have to convert into other things in other situations for more advanced chemistry or physics. It helps with conversions into things like energy and heat. So the other unit is the kilopascal, abbreviated kPa. Now normally, with a metric unit like this, the K would mean 1,000. But we're going to see in just a sec, when we use volume, in certain ways, we need to make sure that we're using the whole kPa. I'll explain that a little more in just a bit. Volume, we're going to measure in liters. Number of moles, clearly moles. And temperature, this will again be in degrees Kelvin. Let's go back to that kPa thing. So, atmospheric pressure is 101.3 kilopascals. Another way to write that would be to say 101,300 pascals. Now, if I wanted to do conversions using the ideal gas law, to keep things nice and clean, if I'm using kPa, I would use liters. If I was just using regular pascals, so converting this K into 1,000, I would need to use meters cubed. Because remember, there are 1,000 liters in a cubic meter. So we're not going to worry about this at all. You just need to be aware of its existence. So get rid of that. We're going to be doing everything just using kPa as our unit instead of converting that K into 1,000, instead of converting kilo into 1,000. So 101.3 kilopascals is atmospheric pressure. But what about this R here? I skipped over that, you may have noticed. Well, R is a gas constant. The benefit of R is that these variables have a relationship with each other through a very specific converting factor. The reason we have this converting factor is because these measurements, remember, they're just measurements. They're made up numbers. They're just made up ways that we can identify things. Bless me. So, so with that in mind, we need to put a number to this constant. So the value of R, if we're using kilopascals, is going to be 8.314. If we're using atmospheres, it will be 0.0, I always need to look this one up, 8206. So at this point, you should have written down the ideal gas law, the variables, the different ways that we'll measure them, and the 2 values of the gas constant that we will make use of. Now let's look at an example. So for our first example, we've got a box. It contains a certain amount of a gas. We're going to have the box is at 150 kilopascals of pressure. It has a volume of 15 liters, and there are 0.75 moles of a gas in it. It doesn't matter what gas it is, whether it's chlorine, hydrogen, oxygen, or steam, water vapor. What temperature is that gas going to be at? It's going to be fully dependent on these variables, not on what element or other properties this gas has. So in order to do this, first thing we need to do is, in order to use this equation, we need the value of that R. So which gas constant are we going to use? Well, we're using kilopascals. So the gas constant we're going to use is 8.314. Okay. So let's plug our numbers into our equation. So once I've got the numbers plugged in here, I can just do some simple multiplication and then divide this side out. Let's just start with one step at a time. So on this side, we get 2,250 equals 6.236T. We're going to divide both sides by this 6.236 so that we can get T on its own. And we get a value of 360 for our temperature. So our temperature is going to be 360. 360 what? It's going to be 360 Kelvin. Let's convert that back into Celsius for a little more of a comprehensive number. So in order to convert it into Celsius, we take 360 minus 273, and that will give us 87. So this gas will be fairly warm, but not quite up to the point where it would be boiling water. Okay, let's do this example as well. We've got an unknown pressure, but a volume of 45 liters, 2.5 moles of gas, and it is at 45 degrees Celsius. First thing we need to do, convert Celsius into Kelvin. That's going to be 45 plus 273. And that gives us 318 kelvins. Okay, so we've got 318 kelvins. Now, we're going to be looking for pressure in terms of atmospheres. So which gas constant are we going to use? We're going to use the 0.08206. So plug all our numbers into our equation. We're going to start with P, which is unknown, that's what we're looking for. V, which is 45, equals N, which is 2.5. R, 0.08206, and T, 318. And let's calculate that. So P 45 equals 65.2. So then divide both sides by 45. And we get a pressure of 1.45 atmospheres. That's all there is to it. For our last example, we're going to look at a certain condition. At a pressure of 1 atmosphere, at a temperature of 0 degrees Celsius, how much volume does 1 mole of a gas take up? This is going to be a very useful concept for doing stoichiometry, because up until now, we've had to do all of our stoichiometry through figuring out the grams, the mass of a gas, which tells us nothing about the actual qualities of that gas. What temperature is it? How many moles? How many atmospheres? What volume does it take up? Because generally we'll store a gas in a container and we can figure out either the volume or the pressure of that. So we call these conditions 1 atmosphere, 0 degrees Celsius, standard temperature and pressure, or STP for short. So if you see STP, you should think 0 degrees Celsius, 1 atmosphere. So how much volume, how many liters is 1 mole at STP? First thing, convert Celsius into Kelvin. 0 degrees Celsius plus 273 is going to be 273 Kelvin. Then what is the value of the gas constant when we're using atmospheres? It's going to be 0.08206. And then we're going to plug our numbers into our equation and find volume. So pressure is just going to be a 1. Number of moles is going to be a 1. R is going to be 0.08206. And temperature is 273. Our 1s, anything times 1 is just itself. So the 1s will just drop out. So we just multiply 0.08206 times 273, and that will tell us what volume a gas will take up at STP. And we get a value of 22.4. So any gas, regardless of what element it is, at standard temperature and pressure, every mole of it takes up 22.4 liters. So if I have 2 moles, if I went up to 2 moles of gas at STP, well then I'm going to double this. I'm going to have 44.8 liters. And I can figure out anything in between just doing that simple conversion. All right?